In this video, we're going to introduce x86 assembly. Essentially, what are computer architectures and the instruction set architectures? First, let's back it up a little bit and talk about a computer architecture at its highest level. A typical computer is made up of several main components. The first is the CPU, or the central processing unit. You then have typically a bridge. Now, modern x86 computers typically have more than one bridge. You'll hear reference to things like the North Bridge or the South Bridge. But the idea is they have a bridge. And then they have memory. The bridge is responsible for handling transactions between the CPU, the memory, and your I/O bus is the other main interface. The I/O bus, the input-output bus, is responsible for interacting with the various peripherals. So think keyboard, CD tray, USB sticks. The peripherals that may be plugged into your computer, that your CPU is going to need to access, that the memory is going to need to access. So the bridge is responsible for the transaction between these main components. Now let's talk a little bit about memory. Memory stores data, and while most times you would consider it fast, it's actually considered moderately fast, and we'll talk about why I'm prefacing that with moderately. You can think of it as a linear array of bytes accessible by their address. So it's a bunch of data that has addresses that you can use to access it. The bridges are the things that coordinate communications between these various buses. The buses are simply the physical means of transferring information. And the peripherals are the things that communicate with the outside world. So anything else your system might need, so something else that you've plugged in to add some enhanced features to your computer. So again, the CPU, I've got the system bus that connects me to the bridge. I've got a memory bus that connects the bridge to the memory. I've got an I/O bus that connects to all the peripherals. So the CPU, or the central processing unit, has several main subcomponents. First and foremost, it processes information. Inside of there, it's also got an ALU, or an arithmetic logic unit. It's responsible for handling the math that the computer is asked to do. Inside of it, it's got registers, which also store data. And here, these are very fast. The register sizes are one word, and they're generally named rather than addressed. So while memory has addresses to access data, the registers inside of a CPU are generally named. And then the actual control unit, which is responsible for executing code. Now, registers versus memory. Now, registers serve the same purpose as memory. In effect, they are ways to store data. But memory is a moderately accessed speed. It's cheap, so you tend to have a lot of it. Registers are very fast when compared to memory, but they're also very expensive, and so there are very few of them on a system. Your program, data, etc. is all sitting in memory, while registers are used to process very small pieces of data at a time. So all of this is normally extracted away from the programmer. The operating system manages processes, memory, files. The processes make it look like your program has full control over the processor and is the only thing executing. Memory makes it look like your process has the specific blob in memory that is fully and solely dedicated to it. And files make it look like you have a sequential series of bytes all to yourself. But the truth is, none of that's actually true. It's all constructs that the operating system is giving you and your applications to make your life easier. One of the main perks of learning x86 is kind of understanding and getting to see the world for how it really is, or getting to see at least the processor in your x86 processor for what's actually happening on your computer. So none of those things are actually true. And by learning assembly, we're going to start to see how computers actually work. Everything on a CPU is done through digital logic. You can think of it as either on or off, or ones or zeros. This includes running your program. A series of bits that controls the CPU is called machine code, and it's just a bunch of numbers that define a set of instructions to run. The machine code for a Hello World program, the most quintessential program that anyone must write, is below. This is machine code that tells your CPU to run Hello World. It's a series of instructions for the processor to execute. But what's that actually doing? Well, that series of numbers is flipping the right transistors to calculate information, fetch data from memory, send signals to the system bus, and then communicate with the graphics card and print hello world. So it's getting additional help from additional machine code, but understand that there's a lot of complex things happening on your computer and your CPU when you request something so simple as a hello world application. Machine code controls the processor on the most detailed level possible. It is moving information in and out of memory, it's moving it to and from registers, it's controlling the system bus, it's controlling the arithmetic logic unit, it's directly tasking the control unit. So we want to directly control the CPU to leverage its full power. It's one of the main goals of writing x86, is I am directly talking to the CPU. But the problem is I don't want to write a bunch of numbers that I can't truly hope to understand. So what I'm actually going to do is I'm going to write assembly. So assembly is a shorthand and essentially a more human readable and legible version of machine code. So assembly uses mnemonics to save us as humans from having to memorize what the numbers in the machine code actually do. So for example, I as a human in assembly would need to memorize sub when I want to do a subtract instead of memorizing the fact that in x86 that's an 83 hex. Or add instead of having to memorize an 81 hex. So as a quick example, we're not going to walk through this in detail, but what you're seeing on the left-hand side is the machine code. So the thing that's actually tasking the CPU, but what you see on the right-hand side is the assembly or the human readable version of that. So the CPU is not actually getting assembly at the end of the day. The CPU is getting machine code. But we as humans read and write it in the assembly level. So writing in pure machine code, it can be fun. It has its uses, though not many, but it is difficult and uncommon. What is much more practical is to learn to write and read in assembly. So an assembler is a tool that then translates from assembly to machine code in a process called assembling. And a disassembler is the exact opposite. A disassembler is a tool that translates from machine code back to assembly through a process called disassembling. So we've got some pseudocode, and we've got some assembly code, and then we've got machine code. So we're not going to walk through each of these. Our goal is just to introduce the concept of what these terminology mean. So pseudocode, you can think of it as the higher level version of the code. What is it you're trying to accomplish? The assembly code is the human readable version of essentially the machine code of how we're going to task the CPU. And the machine code is the actual machine code that will task the CPU to perform that operation. So talking a little bit about the compilation process, when you've been writing code in higher level languages and you compile it, what's actually happening for you is that source code is compiled into assembly code, and that assembly code is then assembled into machine code. And your compiler has been doing all of this for you every time you hit build. So there are a lot of compiled languages out there. So understanding that the assembly we're talking about is not just limited to one or two languages. It's any compiled language that's getting built to assembly code. So what is an instruction set architecture? So the instruction set architecture, more commonly abbreviated to ISA, essentially defines the processors or registers for that instruction set. So instruction set architecture, while this class is focused on x86, right now we're more generically talking about architectures. So an instruction set architecture, an ISA, defines how many processor registers there are to be. So is there one register? Is there 200? Are they 8 bits? Are they 128? So it defines the registers that are available on the process, how many of them, and their size. It defines the address and data format. So I'm going to need to talk to memory, and I'm going to need to do data manipulations. So the ISA defines to me how and what sizes I can do that in. And then it defines the machine instructions. It defines what capabilities does the system have. Does it have the ability, for example, for an add or subtract? Does it have the ability to check for equality? Does it have the ability to halt? So it's all about defining for that particular instruction set architecture, or for that particular architecture, what features or what things can I even do with it. it indirectly defines the assembly language. So it's defining what capabilities I have in the sense that it's telling me I have an add, I have a subtract, I have 5 registers, for example. It's telling me what those registers do. So here's an example of a microarchitecture. And what you're seeing here on the right-hand side is the Intel Core 2 architecture. And this microarchitecture is showing me under the CPU hood how one of these ISAs is potentially implemented on an actual processor. So when I bought, or if you bought an Intel Core 2 processor, inside of that processor, this is the architecture for what was followed to implement that architecture. So a microarchitecture is essentially the way that a given ISA has been implemented on a particular processor. So you'd have the ISA defining the architecture, and then the microarchitecture is actually how they went about implementing that in an actual processor. So collectively, the instruction set architecture and the microarchitecture together make a computer architecture. There are quite literally thousands of ISAs, thousands of microarchitectures, and thousands of computer architectures that exist in our modern technology world. Architectures can generally be broadly defined into 2 main categories. So reduced instruction set, RISC, complex instruction set computing, CISC. So what's the big difference? So RISC architectures are small sets of simple instructions. So RISC processors generally exist for the purpose of they are cheaper to create, they're easier to design, lower power consumption, which results in a physically smaller chip. CISC architectures and CISC processors are large and much more powerful instructions, but that leads to a more expensive chip. It's harder to design, it requires a lot more power, and it's physically larger. So let's take a hypothetical example. I simply want to multiply something by 5. And let's look at a RISC version and a CISC version. So in CISC, a complex architecture, I am likely to simply have a multiply instruction. A multiply is a complicated thing, but CISC is a complex instruction architecture. So I probably just have a multiply by 5. Now a RISC architecture, on the other hand, is unlikely to have something so complicated as a multiply instruction. I can achieve the same functionality, but understand I'm doing it with primitive instructions. So in this case, I'd have to multiply something by itself 5 times to achieve the same result. So you can see one instruction in the CISC took a lot more instructions in the RISC architecture. I get the same result, I get the same functionality, just understand in one of them I had to use very fundamental rudimentary pieces, the RISC, or in CISC I got to use more advanced pieces. Neither RISC nor CISC is better or worse than the other. They both have their advantages and disadvantages. So a CISC instruction may take 100 RISC instructions to implement. As the example we saw before, you may have to take more instructions to implement the RISC one. But a CISC instruction may run at 1/200th of the speed, for example, as the RISC instruction, or consume 1,000 times the power, or take 5 additional years to design. So there's no better or worse. It really depends on what it is that you value from a processor. So talking about some of the major players. So in RISC, the reduced instruction set computers, the main players here, keep in mind there are literally hundreds of thousands, but the main ones you're likely to come across are ARM. For example, this is very commonly used in phones and tablets. MIPS, commonly seen in embedded systems and routing equipment. Things like PowerPC, which were original Macs and Xbox 360. The CISC instructions, so the complex instruction system computing, x86, which is what's commonly in consumer computers, the Xbox One,